All right. Morning, everyone. So we're going to start talking about the operating system today. It's the last project in your book, and it's split into two projects for this class. So 12A and 12B. You are here. So 12A, which is the first part of the operating system that we're going to talk about today, is due on Monday, like a week from yesterday. 12B, with the second part, which we're going to talk about on Thursday, is due the following Friday. And I also wanted to draw your attention to the fact that so maybe you can't see that, maybe it's too small.
Okay. Time to get calculated.
So I know it's a little bit early in finals, but basically this is the Tuesday, May 3rd, which is the first day of finals.
Mhm.
That's like when the final exam for this class would have been. And partly because of that, and partly just to make sure that my grading is kind of staggered out through finals, so I don't have like everything dumped on me all at the end. Tuesday, the first day of finals, is the last day that you can like request an extension to. So everything has to be turned in by then. All right. Let's start talking about this project. So basically, let me just talk a little bit about the kind of the mechanics of how this project is going to work. And we'll talk a little bit about kind of operating systems in general, and then look kind of specifically at the different pieces of the Jack operating system and what you need to do. So basically, there's 1, 2, 3, 4, 5, 6, 7, 8 Jack files. So this is going to be, in some ways similar to Project 9, where you'll be writing a bunch of Jack code. Different though, because it's the kind of code you're going to be writing is very different, right? So you know how usually when you have some VM code and you load it in the VM emulator, it says, "Hey, I can't find these things. Would you like me to use the built-in things instead?" And you always say yes, right? So what it's talking about there is the operating system files. So basically, any of these files, with these specific names, sys, array, string, keyboard, whatever, if you have a file called, say, sys.vm in the current, in the same folder where you're trying to run some VM code, it'll use that instead of the built-in sys operating system file. So in theory, at the end, when you're trying to run Pong with your complete version of the operating system, you compile Pong, so you've got like pong.vm, game.vm, I don't know, there's like a few things, and then you copy paste all of your, sys.vm, array.vm, string.vm, like you compile all those and copy them in there, and when you run it, it'll now be using all of your implementations of the operating system functions instead of the built-in ones. But the nice thing for this project is that it can do it kind of on a file-by-file basis. So if you copy in math.vm and you run something, it'll use the built-in versions of everything else, but it'll use your implementation of the math functions. And this is how you're going to test these as you're going, because they all depend on each other. Like, string, some of the functions in string call output, and some of the functions in keyboard call string, and whatever. So that'll be fine. You can just test them one by one. Okay. We'll talk more about this when we'll look at some specific things. There's some error codes here, which we'll talk about later, but this is just for your reference. It's in the book. I don't know. It's just in case you want to look at that. All right. So let's see. I don't know whether to see if this works. So it's like, I kind of want to like write some stuff on the screen, but I'm also going to look at some files, so. It crashed, no. Wait, my choices are delete or restore. Like, I don't want to delete anything, I just don't want to. Delete, okay. So let's see if I can make this work. All right. So, what is an operating system? And if you really want to know, I'm not an expert on operating systems. If you really want to know, you can go take Dr. Affair's operating systems course, and tell you all about it. But I think really, from my point of view, there's kind of two main things that an operating system does. So, well, really, the main thing it does is it mediates between hardware and software. Okay, so there's the actual hardware that does stuff, and then there's software you want to run on your computer, and the operating system kind of provides a layer in between. So when you're writing your code, you don't have to directly, do stuff with the hardware. The operating system kind of provides some instructions. So part of that is managing access to shared resources. And this is a big, big part of what any actual operating system does, because, as we all know, you can have a bunch of programs running on your computer all at once, and they all want to access, maybe multiple programs want to print at the same time. They all need access to memory. They all want to run. Like, actually, the CPU is a shared resource, because all these programs are trying to run. They can't all run at the same time. So the operating system kind of makes them take turns, right? The network, the disk, right? So, like CPU, network, disk, RAM, printer, ... right? All of those things are shared resources, and the operating system is responsible for deciding which programs get to access what things when, making them take turns, stuff like that. Right, so therefore that means, like, for example, if I am a program that's running and I want to print something, I don't have to worry about saying, okay, let's figure out, is anyone else using the printer right now? Then maybe I'll wait, and I just call an operating system function, operating system print. And it's like, sure, I'll do that, I'll get to it. And then the operating system probably keeps like a queue of jobs that are waiting to be printed, and it manages like what the printer's doing, all that. But as a program, I don't have to worry about that. I just hand it off to the operating system, and it deals with it. And then, very related but kind of different, is just providing services. I'll just say to make using resources easier. Okay, so actually that example I just gave about printing is kind of an example of both. It's both managing access to the printer, but it's also providing this service that I don't have to worry about, how do I actually talk to the printer, how do I, imagine you could have, there's hundreds of different kinds of printers, and you have to talk to them all in slightly different ways, and the operating system deals with all that. It just provides like a nice function I can send it a PDF file, and I say I would like this to be printed. Please do so, and it handles all the details, right? So that's just making it easier to access those resources. So for project 12, with our Jack system, I guess it's the hack system, the Jack language, we're only doing this part. There's no such thing as shared resources, because there's like, there's only one program that can run on the computer at a time, and so this isn't really a thing. This is a big part of what real operating systems do, but we're not talking about this part because we're not talking about having multiple programs running on a computer at the same time. That certainly would be a big part of what you would talk about in an operating systems class. But we're basically just doing this, right? There are these resources that the hardware provides, like, you know, there's a screen, and you can draw on the screen by setting bits in memory. Okay, but setting bits in memory sucks. I want to say things like, print the number 12 on the screen. I don't want to think about which bits have to be set to make some pixels appear to make the number 12 appear on the screen, right? So that's a service that the operating system is going to provide. So there is, in fact, I can say output.println. And literally, there is some code that figures out exactly what pixels to set on the screen to make that happen. Okay. So that's what we're going to talk about. Any questions at this point? Since I guess I should say another big thing that operating systems do, which maybe you could really see as an instance of the first thing, but is like enforce, you know, security and access policies. Right, so the operating system kind of has permission to access anything and do whatever the heck it wants, right? And the operating system can create some rules or enforce some rules that, like, you know, certain programs are only allowed to access certain things, only allowed to access certain files or do certain things. But again, that's also not, we're not going to deal with that. So this is Project 12. Just that part. Okay.
Yay.
What was that?
Yay.
Yay, right, yeah. Okay, so let's see. Let's see. Okay, so if you look in the Project 12 directory that comes with the NAND2 Tetris materials, this is what you'll see. So, so there's a bunch of .jack files provided for you already. So this is nice, and it we'll look in them in a second. But basically, it's the outline of, it's just a bunch of functions there that aren't implemented, and you just have to implement them. Okay, so it tells you exactly what you need to do, and there's also a bunch of tests.
Sorry for comments.
What was that?
Sorry for comments.
Yeah. We'll look at the test in a minute, but let's see. So the first one I want to look at is sys. Okay. So sys has 4 functions in it. So the first one is the famous sys.init. So if you recall, part of what our, let's see, at what level does this happen? It's actually the, oh, now I forget. Something called sys.init. That's like the first thing that happens, right? Is it? I guess it would be, yeah, I forget. Anyway, I'm blanking at the moment on whether it's the compiler that generates that code or whether it's the VM translator. But somewhere, right, the very first thing that has to happen is a call to sys.init. And what does that actually do? It basically, so over here. So here's sys init. So it's going to do a few things. It's going to call all the other init functions. Okay, so you'll see that All the other operating system files, like math, keyboard, output, whatever, they all have an init function. And it's just gonna and because maybe they have like some static variables that they want to set up with a certain value or whatever. And so it'll just call all of them. Not all of them might do anything. So some of them might not actually do anything, and it's kind of up to you whether some of them, maybe it would be nice to do it, but you don't have to. But this is just going to call all of them, whether they do anything or not, just so that they'll all get initialized. Okay. And then it's going to call main.main. And then it's going to call sys.halt. That's it. Okay? So that's the reason that we didn't just call main.main in the first place, is because we want to make sure that we have a chance to call all these other initialization functions to set up stuff in the operating system. Okay? Halt. What does halt do? There's actually no way to stop the computer. Right? Once you start it running, it's just going to keep running forever. So what halt will do is go into an infinite loop. At least then it'll like stop in the sense that it's just like running the same. It's not just like, but I don't know. Halt.
True.
Do an infinite loop.
Empty bracket.
I trust that you all can figure out a way to write an infinite loop on purpose. There's this wait function, and this wait function, well, I guess that doesn't work. The wait function is extremely unsatisfying because it says, oh, if you want to wait for, you give it a duration which is in milliseconds, and then it's supposed to wait that long. Okay, now, real operating systems have functions like this, and really what that's doing is mediating access to the resource of your hardware's clock. Okay, so all real computers have a clock. You probably know this, right? Your computer can tell you what time it is. And really what's happening is that, there's a physical little like piece of quartz crystal that you put a certain electric current through it and it vibrates at a very specific frequency. And by counting vibrations, it's able to kind of keep track of how much time has passed. Don't ask me any more questions about that. I don't understand anything more than what I just said. There's some magic physics that happens, and it's able to, yeah. But obviously the hack computer does not have that. There's nothing in the hardware that we built that keeps track of time in any way. So what this is supposed to do, you literally put some code in there that you loop for a certain number of, maybe you're like, oh, I multiply the duration by 20 and I loop that many times. And you should try it and then see how long it takes on your computer and then adjust it until it's about right.
Cool.
I mean, yeah, it's and obviously if you like sent this to someone else and they ran it on their computer, if their computer is much faster or slower than yours, it's going to be different. So you just calibrate it for your computer and good enough. Right. At least it means that if you were like coding a game in Jack on your computer and you needed like some pauses to have it, do the right number of frames per second, it would be about right on your computer. But yeah.
So then do we not need to worry about it not working on your computer?
No, you don't need to. Yeah. I mean, like, I'm not gonna. So, like when I'm grading this, there is a test, and I'll show you the test in a second. The test is basically like, hit any key to continue, and then it's like, okay, waiting 2 seconds, and then it says wait 2 seconds, and then it prints out done. Make sure that took about 2 seconds, right? That's the test. I will run that, and if it waits some amount of time, like I'll be like, great. I'm not gonna be timing it. Okay, so if it doesn't wait at all, then I'm like, okay, something is wrong. If it like waits for an hour, then that's not good. But yeah, just
Your
like
computer would like kill me.
loop a bunch. That's all. All right. Error. we're just going to, you're given an error code, which is an int, and you're just supposed to print out ERR and then that int. So it's just going to print, for example, like ERR6, and then call sys.halt. Okay. Which, so here's an example of all these files using the other ones. So like, how do you print ERR6? Well, you have to call output.printString and output.println. So that's using functions provided by output, but that's perfectly fine. And if you start with this, as I recommend, then you'll be testing your sys.jack, but it'll be using the output version provided by the default version, and that's fine. There's a list of these error codes. You don't need that for literally all this has to do is print out the letters ERR and then whatever number you're given. Okay, you don't have to print out like a string explaining what the error means. Although I suppose you could if you really wanted to, but all right. Any questions about this? This one's pretty straightforward. Okay. So actually, before we move on, let's just look at the test that comes with this. So again, so the tests for sys are in the sys test folder. The reason it's in a folder is so that what you're intended to do is to copy in your sys.jack into here. You have to run a compiler on it to generate a sys.vm file. And also, you can just run a compiler on the sys test folder. And it'll generate your sys.vm, it'll also generate like a main.vm there's a main.jack file in this sys test folder. And if you've finished your own compiler and you wish to use your own compiler, you may. But you're obviously certainly welcome to use the Jack compiler that comes with the Nantu Tetris materials, right? You can definitely do this whether you've finished your own compiler or not. And the reason it's in a folder is so that you can copy this in here, and then when you load it, it's only using your sys. It's not using like all these other ones that you haven't finished yet, or they don't work or whatever. Because if you ran it just out here in this folder that had all of these other operating system files, it would try to use all of yours, and it wouldn't work if you hadn't actually finished all of them. So, here is the main.jack in the sys test folder. So you can see this test, actually it's only testing weight. It says, all right, weight test, press any key. After 2 seconds, another message will be printed. And then you press a key, it waits for you to press a key, and then it calls sys.wait 2000, and then it prints another message and says, time is up, make sure that 2 seconds have elapsed. Now, of course, so it's testing weight. It's really kind of testing init also, because like this won't even happen if you haven't implemented init, because init has to call main.main, right? So if you haven't implemented init correctly, then it won't even run at all. But how do you test halt and error? I mean, like, I don't know. You could write your own test. You could pretty easily put some more code in here, or make another file. Or just, eventually, as you test it with other things, it'll be testing those as well. So those also aren't that hard. So, all right, let's next look at array. So array is actually very, very simple. Because arrays in Jack are very, very low level, right? They're literally just a memory address, and then you can just access things at that memory address, right? In other languages, like, think about in Java, if you make an array, you can ask for its length, you can, you can have a for loop that works over it. There's various things you can do with arrays, and so there's a little bit more abstraction that's provided. And certainly Python lists, Python lists have tons of code. You can do all sorts of operations on them, right? But Jack arrays, literally, it's just a memory address. So there's not much to do here. So if I say I want a new array of a certain size, all you're going to do is call memory.alloc. You're just going to allocate some memory. That's it. So new, just call memory.alloc. And return it, right? And dispose. Yeah, I call memory.dalloc. What do I call memory.dalloc on?
This.
On this, exactly. Basically, all this does, it lets us treat individual arrays as if they are objects, so that we can call the dispose method on them. I can say I'll make a new array A, and then I can say a.dispose. But then all that does is just calls. You could also just say memory.dalloc A, and that would work. But this makes it look slightly nicer. Any questions about this? Let me show you the test. So, it just makes a bunch of arrays with array.new, and it does some operations on them, and it calls, .dispose on them, etc. So, there is a fun thing about this if you look carefully at what's happening. So here's a variable r. It says let r equal 8,000. Seems reasonable, right?
Yeah.
Except notice that r is an array.
I don't like that.
Wait, what? And then over here it's like r0, r2. So you could totally do this in Jack, right? Everything is just a 16-bit value, so I can make an array. Nobody cares what type I set it is. I can just assign an int to it. So literally, that's making an array that just points to memory address 8,000. So you should not do this. You can do this in C also. Jack isn't particularly special in this regard, but again, very low level, right? It's giving us direct access to the memory. Right? Arrays just are convenience on top of that direct access. It's not really hiding anything from us. Yeah, Gary.
So in this example, you would not be able to deallocate R for anything of the sort.
Oh, you could. I don't know what it would do.
No.
If I said memory.d or if I said r.dispose, that would work fine because it would say, okay, this is a method call. What type is R? Oh, it's an array. Okay, so I know I need to call the array.dispose method, and that would call memory.dalloc on R, and it would call memory.dalloc on memory address 8,000, and then however dalloc works, we're going to talk about that on Thursday. But it would go and it would assume that memory address 8,000 was some area of memory that it had allocated, and it would try its best to deallocate it. But probably it would crash at that point, maybe, because whatever it's expecting to see there is not what's going to be there, right? So yeah, you could, but I don't even know if it would crash. It might not actually literally crash, but it would do something weird, and things would just get messed up. Yeah.
So, what if, say, A is allocated at memory address 8001?
Yeah. So there's a part in so Roald Dahl's book, Charlie and the Great Glass Elevator. I don't know how many of you read Charlie and the Chocolate Factory and then Charlie and the Great Glass Elevator. So there's a part where they're riding the elevator around the factory, and you know, Charlie finds out, Willy Wonka mentions that there's a second elevator in the factory, but they ride on the same track system. And Charlie's like, what if they run into each other? And Willy Wonka's like, well, they never have. So, yeah, that's the answer.
Oh God.
All right, let's move on to the next
This is why
module.
we had nice things. I'm not ready to do a square root for math.
Square root, yeah, we'll get there. All right. So let's talk about strings. So there is actually quite a bit of interesting stuff to implement here. So string.
Well, string has a length, but it really doesn't.
So what is a string, right? How do you store a string? Of course, it's just maybe an array of characters, right? So there's a constructor here, and it says okay, we're going to make a new string, and it takes a max length as an argument. So, of course, you know, in Python or Java or whatever other language, when you make a string, it has whatever length it has, and you know, there might be a way to like append characters to the end or not, depending whether it's immutable or not, but there's no like specific maximum length, right? Or think about like array lists in Java or lists in Python. You can always append more stuff to the end, but as you know, the way that works is when you run out of space, it actually has to go and allocate more, you know, a bigger place to store things, copy over the old data, and then, you know, deallocate the old one. We're just not going to bother with that. Okay, I mean, we could. There's actually no reason in principle that we couldn't make the string class do that. But the way that it's going to work is you just have to say up front, how big could your string possibly get? So this is not the length of the string, it's the maximum length of the string. It's like how much space you're going to pre-allocate for it. But it says, okay, the maximum length is this, but the initial length of the string is 0. So it creates an empty string that like could eventually get this big, but is currently length 0. So that suggests that just having an array of characters is not enough. We also need a field to keep track of the current length of the string, right? Just like you would, you know, think about how array list works. It's got like some amount of capacity, and then it has an actual length. It's like we're actually using this much. Okay, so you will need, you know, a field for the current length. And you will need a field for an array of characters. And obviously, the constructor has to initialize those using, for example, array.new, right? Dispose, of course, disposes them. All right. Length is easy. Char at, set char at, append char, and array / char are all fairly straightforward. They're just like looking up a certain index in the array. So like char at, it just has to look up index j in the array and return whatever's there, right? Set char at is just setting something in the array. Append char, right, is it needs to use the current length to figure out, you know, where do I put the new thing, and then I'm going to increment the length. Erase char is opposite. The one thing these all do need to do, though, is they need to do some error checking. So if we look at down here at the list of error codes, notice that, oh, actually, string.new, it says it can generate an error as well. If you give it like a negative length for a new string, it's like, no, cannot do that. So here's char at, set char, dependent, blah, blah, blah. So, you know, if you say, oh, what I made a string of you know, and it has length 5, and then I ask, what's the char at index 29, right? You could imagine if you just don't check for that at all, it'll just try to look at index 29 in the array, which will be an error because Jack checks whether the index of, no, I'm joking, of course it doesn't. No, it'll just like look 29, you know, memory locations past the start of the array, wherever that is, and it'll just return whatever's in memory there. So it wouldn't be an error, it'll just give you junk. But we're going to make char at so that it actually checks the index that you give it. And if you give it an index that's out of bounds, it'll generate an error instead of returning garbage. So I'll just say, you know, this is char at, set char at, append, erase. You know, they all do index bounds checking. I guess erase last char isn't doing, and append char aren't doing like index checking, but they're checking, you know, append char has to check if the length of the string is already equal to the max length of the string. So I guess actually maybe you have to remember what that max length was, because once you allocate an array, you cannot find out from the array anymore how long it was allocated to be. Right, so you have to remember what that max length is. So I guess we'll also need field for max length. And then the erase function will have to check if it's currently empty, then you can't erase another char. Okay, then there's a function int value. Well, let's talk about these ones first. These ones are very simple. Because you know, in string literals in Jack, if I have double quotes, there's no such thing as escape sequences. Like, you know how you can do like \n in most languages to have a new line character in your string? Jack doesn't have that. So if you want to know like what, I want the character which is the new line character, there's no way you can write it by like, you know, putting quote \n or whatever. So you can say string.newline and it'll return you that character. So how are we actually going to implement this? Well, characters are just ints. So we just return whatever int newline is. I think it's 128. But you can look in the book and it'll tell you what number it's supposed to be. So we don't really need this technically. We could just always say 128 everywhere that we wanted to talk about newline. But it makes your code look nicer when you say, you know, instead of saying while c is not equal to 128, you say while c is not equal to string.newline. And then everyone can see that you're talking about new lines, right? So those are easy. So the only ones left to talk about are this int value and set int. So these ones are actually doing some interesting work. So int value says we have a string that supposedly represents an integer, like it has some digit characters in it. And we want to turn it, actually read it and turn it into an int. And then set int does the opposite. We give it an int, and it's going to set the characters of this string to be, you know, digit characters to represent that value. So how does this work? Int value and set int are for converting from int, between int and string. And I guess converting from string to int, I guess that part at least, if you've implemented the tokenizer, and I think we've done that before, right? So the tokenizer had to do that because as it was going through character by character, and when it was seeing digits, it had to like basically convert it to an int so it could return that as a token. But let's talk about how to do. We'll talk about that a little more because there's a little more to talk about here. So let's talk about converting from. Oops. string to int. So first of all, we're going to loop, as long as character are digits. Well, how would we test whether a given character is a digit? We can't. So like if I was doing this in some other language, I might say like, oh, if the character 0 is less than or equal to my C, and C is less than or equal to the character 9. But we can't say like single quote 0 or single quote 9 or whatever in Jack. There's no way to write down characters. So we just have to use whatever their integer codes are. So it turns out that 0 is 48, I believe. Did I get that right? Yeah. And 9 is 57. And this is standard ASCII code for these. So we basically have to say, okay, as long as 48 is less than or equal to my character C. Oh, except we don't have less than or equal to in Jack. We only have less than. So I guess you have to say 47 is less than whatever. And then for each character, so if I see the character 1, then I'm like, okay, currently I have the number 1. Now let's say I see another character 2. So what do I do with that new number 2 to know that now my current value is 12? I can't just add it, because that would give me 3. That doesn't make sense. In general, what I can do is say, take my current value, multiply it by 10, so that kind of means like shifting it over, putting a 0 on the end, and then I add the new number that I just got. Okay. So we're going to keep track of the current value. For each new digit, current value equals 10 times current value plus the digit. Okay, well, plus the value of the digit, like 0 through 9. How do I convert a character 0 through 9 to its value as a number?
Take whatever its code is and subtract it from the code from 0.
Exactly. I can, if I subtract 48, right? So, if I have the number, the character 1, that's code 49. When I subtract 48, I get 1. This is just subtract 48 from character. Right. So probably when you did this in your tokenizer, you didn't have to do all this stuff, because you could, for example, just each digit character you saw, you just like added it to a string, and then at the end, when you wanted to return an int, you just converted it to an int using some thing provided by the programming language, which of course was doing this under the hood, but we have to implement this ourselves now. Okay, how do we convert from an int to a string? Well, there's an easy way to find out what the last digit of a number is in base 10, which is I ask what the number is mod 10. So if I have the number 4,237 and I do mod 10, I just get the 7. That's always going to be the last digit, right? So to get the last digit, we'll do mod 10. And then I can get rid of the last digit by dividing by 10. So if I, again, if I have 4,237, if I divide by 10, it would be 432.7, but it rounds down, so it's just 432. So dividing by doing integer division by 10, we'll just like chop off that last digit, right? We can chop off last digit by, I'll write this as like mod 10. This is dividing by 10. And then we just can keep repeating this to get, all the digits one by one. And I'll say repeat, loop until 0. So if I start with some number and I keep dividing by 10, I'll know when I'm done when it becomes 0, right? Because if I had, say it was 7, I say, okay, 7 mod 10 is 7, that's the last digit, then I divide by 10, I get 0. And now I'm done, because I got 0. There's a few issues though. Number one, this gives us the digits in reverse order. And we need to put them in the string, like with the biggest digit first. Yeah. The other issue is we don't have mod.
Yeah.
Right? So let's talk about that one first, actually. So wait, mod. It is possible to implement mod using only the things that Jack provides. And some of you, I think, figured this out on Project 9. But it's not too hard, actually. If we have, let's say A mod D is the divisor. Well, let's think about this. If I take A divided by D, so that tells me kind of how many times D fits into A, rounded down, right? So it's just the whole number of times that D fits into A, and there would be some left over. If I multiply that by D, let's say that D fits into A 5 times with some left over. Well, if I multiply that by D, that's kind of that amount that fits into A with just a little bit left over. So now if I subtract that from A, I'll get that leftover part. Right, so this is how you can do, this is assuming this is integer division that rounds down, right? If you just look at this and you're like, well, A divided by D times D is A, and then A minus A is 0, right? Yes, that would be true if this is, normal division. But if it's integer division, this isn't 0. This is the mod. So you could just kind of do this in line. Personally, when I did this project, I actually made a mod function in the math class, just because I was like, maybe I'm going to want it a few different places. So I made up my own math.mod, and I just did that, and then I could use mod. And you're welcome to do that, right? So like there's certain functions that you're required to implement, but you can certainly add your own extra functions, as you wish. Yeah, the other thing is, okay, how do we deal with the fact that it's reversed, right? So if I just naively kind of do this loop, keep getting the last digit, I'm going to get the digits in reverse order. There's a few different ways you could deal with that. One is, you could just put them in the string, in the order that you get them, and then at the very end, go through and reverse them. That's a little annoying, but maybe the most conceptually straightforward. To just say, well, I'm just going to have this loop, get the digits one by one, and then they're going to be in reverse order. So at the end, I'm going to, and maybe you could even make a new string method called reverse that would reverse the digits, reverse the characters of a string. It's kind of a fun exercise. So I'll just say how to deal with reverse order. So we could reverse the string. Another thing you could do, which is how I did it, and I am personally fond of, is using recursion. Of course, right? So how this works is you get the last digit, and then you recursively convert n divided by 10 to a string, and then you append the last digit. right? So you kind of, by using recursion, we're able to hang on to what that last digit was, go ahead and convert the rest of the number first, and then as the very last thing, that digit that we saved in a variable, we'll append it to the end of the string. So that way the recursion is kind of keeping track of all the digits for you at once, and then like appending them in reverse order as it comes back up. There's probably other ways you could, maybe you can like go through, first have a loop that goes through and just figures out how many digits there are going to be. And then once you know how many digits there are going to be, then you could start putting the digits in the string kind of from the end. There's different ways you could do it. You're welcome to do whatever you want, as long as it works. One big thing that we have not talked about with both of these is they have to deal with negative numbers too. Okay. So I will just say, note, handle negatives. So, for example, for converting a string to an int, what I recommend is, you first have a check and you see if the first character of the string is a hyphen character, is a minus symbol, right? Then you just set a variable, like a Boolean variable, to remind yourself that the answer is supposed to be negative. Then you do all this stuff the same as you would have otherwise. And then at the very end, you have another if that says, oh, if my Boolean was set, that means it's supposed to be negative, and I'll just negate the answer before I return it. Right? And same thing here. So for converting an int to a string, I would say first check if it's negative. And if it is, remember that fact, and then take the absolute value. And then all the conversion happens on a positive number. And then, well, I guess actually for converting to a string, you say if it's negative, I will go ahead and immediately make the first character of the string a hyphen, a minus sign. And then I'll take the absolute value of the number, and then I'll go ahead and convert the rest and append all the characters. So again, the key idea is, yes, you have to deal with negatives, but you want to deal with it separately. So you kind of handle the case of whether it's negative or not, and you remember that. Then you deal with, the main algorithm is only dealing with positive stuff. And then maybe you have to fix it up at the end or something. And we'll see that the same thing is going to be true for multiplication and division and stuff like that. All right, I think that's all I wanted to say about those. Any questions about these? So this, I find this fun because I guarantee, that any programming language that you've used, somewhere in either the implementation of the language itself or in its standard library or whatever, there is code that does exactly this stuff. So it's fun to have to write it yourself, and you kind of gain a little bit more appreciation for what, what happens when you call the int function in Python to convert a string into an int. Or what happens when you say, print some int on the screen. Okay, and then what is next? Keyboard. So, the first function in the keyboard class is init. However, and this is kind of general advice, don't start by writing the init function. Because you don't necessarily know what you need to initialize. So, as you go writing other stuff, maybe you'll find, you're like, oh, in order to do this, I'm going to want a field, right? Or I'm going to want some static variable that is going to keep track of something for me. And if you end up wanting that, well, fine, then you can go and fill that in, make the init function, initialize it however you want. You're not necessarily going to need to put any code in the init function in every class. For the keyboard class, personally, I was looking at my solution this morning. I personally did put some code here, but as I was looking at it again, I thought of a different way to do it that doesn't need to put any code in here, so whatever. So what else do we have in the keyboard class? What is... So here's the key pressed function. So if you look at the comment here, it looks like it's going to be a lot of code because it looks like maybe we're going to have a lot of ifs or something. But that's not true. So this comment is really more kind of aimed at someone who is using this function, not for the person who's writing the function. So it's just saying, hey, it returns the character of the currently pressed key on the keyboard. If no key is currently pressed, return 0. So again, even that statement makes it seem like we're going to have an if in here, except if you remember, that's literally how the hardware works. There's a certain place in memory that when a key is currently pressed, the value in that place in memory is the value of the current key. And if no key is currently pressed, the value is 0. And it just says, hey, it recognizes all ASCII characters as well as some special keys. But again, this is literally how the hardware already works. You know, when you press down arrow, the value 133 shows up in that place in memory. There's actually no ifs you have to do. Literally, the only thing you have to do here is there's a function in the the memory file called memory.peek. And you can tell it an address you want to look at, and it just lets you read that location in memory. So all you have to do is call memory.peek on the location of the keyboard, which is 24,000, whatever it is. I don't remember what that number is. So keyboard. So key pressed. Right, we're just going to call memory.peek. 24,576.
Ooh, I was close.
What was that?
Ooh, I flipped the 6 and the 5.
Oh, yeah. Easy to do. Okay, then there's like, let's see, what else do we have? So that's like extremely low level. And we're going to see that the keyword class we're going to build up nicer abstractions on top of these things. So read char is slightly nicer than key pressed. So read char actually waits until a key is pressed on the keyboard and released. And then it prints that key on the screen and returns what it was. Okay? So obviously calling key press directly, it's like I can find out, are you pushing a key right now or not? But if I'm like, yeah, I want to wait for the user to hit a key and tell me what key it was, then you want this. And obviously it's going to have some loops. And you've seen loops like this in some examples we've done where it's like, okay, while there's not a key pressed, then we're going to wait, and once the key is pressed, we're going to wait for it to be released. There's actually some, there's pseudocode in your book for this. Oh, my pen stopped working. All right.
It's that time.
I know it is that time. And I guess actually this is a good opportunity for me to say. So yeah, so if you look in your book, you'll find, I think it's figure 1210, has some pseudocode that kind of explains how this is going to work, if you want to look at that. Do read chapter 12 in your book. And the annoying thing that I found about it is that it kind of, like, it organizes things by, I don't even, it's like there's a section that talks about the general principles behind things and kind of the big high-level algorithms. Then there's a section that talks about kind of like some of the lower-level implementation details. And there's a section that talks about, what you actually have to do for the project. But the problem is, I mean, that kind of makes sense on one level, but the problem is that, if you're like, I'm trying to write the keyword class, I'm looking for any information and help the book can give me about writing the keyword class, you have to look at all three of those places, because there might be some kind of high-level algorithmic stuff that it talks about, and there also might be some low-level details that it talks about. There also might be something where it's like, oh, specifically for your project, here's what you should do. You have to look at all of them. So it's unfortunate. It's not. It would be nicer if it was organized by class, and then for each class, it maybe said, okay, first let's talk about the high level, now let's talk about some details, but it doesn't do that. So,
Cogitation.
I definitely, when I was doing this project myself, I found myself flipping back and forth. It was like, I remember reading something like this. Where was that? And it's like, so you just have to look through it and see, whatever you can find about each class. So, because a lot of these do have like a little like figure with some pseudocode, or will describe an algorithm or whatever. In many cases, the book kind of does help you give some hints as to how to implement these. So read char, say C pseudocode in the book. I think I want to say, let's see. And of course, to write to the screen, it's going to use output. Read line is interesting. So let's see what it says. It says displays the message on the screen. Okay, so you're just going to say output.printstring. Reads from the keyword the entered text until a new line character is detected. It echoes the text to the screen and returns its value. Also handles user backspaces. Okay, nice. So obviously it can use read char to read each individual character. And like when it says it echoes them to the screen, well, read char is going to do that. So read char, you can call read char in a loop. It'll read each character, echo it to the screen. But then we need to return a string. So you're going to create like a string buffer in here. And every time you call read char, well, you check. If it's a new line, then you're done. If it's most other things, you can append that character to the string and loop again. If it's a backspace, you have to. So this is what there's an erase last char method in the string class, right? That erases the last char. There's also the output class has a function called backspace that will move the cursor back a space and like erase whatever was on the screen there, okay? And you need to do both those things. So read line, you're going to call read char in a loop, and then if backspace, you're going to erase last char from buffer, and output dot backspace. It definitely does not support like using arrow keys to move back and forth inside your input to edit it. And after you've written this, if you can contemplate what some library is doing to let you, like when you're typing something, to let you actually like use the arrow keys or the mouse to like click in the middle of what you typed and like backspace it, edit it. It's doing some pretty sophisticated things to keep track of what you've entered and let you edit it before you hit enter. So I mean, in theory, you could add that. Might be a fun thing to try to add. That it would also like detect arrow keys and let you like move stuff around. Yeah.
Should we worry about resizing the string buffer?
That's an excellent question, right? Because you're like, well, wait, if we need a string buffer to store the input, how big do we make it? Because when we construct a string, you have to say what the maximum size could be. Yeah. Just decide what you think a reasonable size is. So maybe like, I don't remember what the number is, but there's some number of characters wide the screen is. Maybe just be like, one screen width full of text should be enough. So we'll just make it that big. And if you want to enter more than that, tough. That will certainly be big enough for everything that that you're in the test that this is going to do. It's a trade-off though, right? Because you can make it much bigger, and then it lets people enter bigger strings. But then that means that every single time you want to read some input, it's allocating a bunch of memory for that string that's not going to get used, right? Obviously it would be better if our strings could be resized dynamically, And then we could allocate it small, and as you typed more stuff in, it would get bigger. But we don't, again, we could do that. That actually wouldn't be very hard, but it's not required. Read int. Read int really is just going to call read line and then convert the string to an int. That's all it has to do. It looks complicated, but if you read this carefully, you'll realize that most of the stuff that's described here is already done by those other functions. So, all right, we've got a few minutes left, so let's just talk briefly. I'll start talking about math today, and then we'll finish it up on Thursday, I think. But let's look at math, because math has some interesting stuff that we have to do. Again, init, it's up to you. There's ways to do this that you don't really need to do any initializing. There are other ways to do it where you might want to create, for example, the way that I personally did it, I found it useful to have an array that was preloaded with all the powers of 2. It just made things more efficient, so I could just look up powers of 2 instead of having to compute them every time. So my init function just created that array and filled it in with the powers of 2. And then that ran once at the beginning. But you don't have to do it that way. So there's this abs function. So absolute value, min and max. Max, min. Those are all easy. Okay, do those first. Get them out of the way. It's like a few lines of code. The interesting ones, of course, are multiply, divide, and square root. So let me say first that as long as they work and give the correct answer, it doesn't matter how fast they are. Okay? In terms of like whether you get credit or not. Now, we will spend some time talking about how to do these efficiently because it's interesting and you might like to try. And your book does describe, it gives you some pseudocode and it helps you kind of figure out how they work. Because obviously any real operating system or hardware or whatever is doing these efficiently. But, for example, for multiply, it is perfectly okay if you do the thing that we did like on project 4 where you had to write some assembly code that just like, x times y, sure, let's just loop x times and we're going to add y to a variable every time, right? That is x times y. And you know what? Because these are only 16-bit values, the biggest possible 16-bit value is what? Like 16,000 something, or I don't know. Looping 16,000 times? It's not that big of a deal, right? If these were like 64-bit values, you do not want to do multiplication this way. It's like, oh, sure, you want to multiply, 2 billion times something? Sure, let's just loop 2 billion times, and I'll get the answer to you, next year. But,
Go bird.
Actually, no, 2 billion, it wouldn't take that long. But no, but I mean, you can implement it that way if you want. Divide, how do you do divide in a, what's the stupid way to do divide? The stupid but correct way to do divide. You just do repeated subtraction instead of repeated addition. Okay, so you say, all right, x divided by y, I'm going to keep subtracting y from x over and over again, and I'm going to count how many times I can do that until I get to 0. And then that's your answer. Square root. What is a simple and easy way to do square root? Morgan, what do you think?
Could you try to work from 0 up to your number and square everything and see if it matches?
Yeah, exactly. So you say, all right, what's the square root of 29? Well, 0 squared, that's less than 29. All right, let's try the next one. 1 squared, that's also less than 29. Let's keep going. 2 squared is 4. 3 squared, 4 squared, 5 squared. You say 5 squared is less than 29. Oh, 6 squared is too big. Okay, so the answer was 5. Right? And that's actually, I mean, that's not as inefficient as it sounds, especially because, you know, we're talking about now we're taking the square root of a 16-bit value. That can only be, you know, like an 8-bit value at most. So we only have to try like 256 things before it'll get too big. So it's not that bad. The book suggests that you do like a binary search, which is faster, which is kind of fun. But so you kind of like, you're like, oh, this is too low, so let's like jump up and try something higher. And oh, that's too big, so we'll zero in it. You know, that's a little faster, but not necessary. All right, so yeah. So in theory now you have everything you need to implement to do project 12A. Next time I do want to spend a little bit of time talking, at least multiply, because it is interesting thinking about how can we actually do multiplication faster than that, and you know, and how do other real systems do it? How can we do it in Jack? And then we'll talk about the other parts of 12B. All right, see you on Thursday.
Period.
Ooh, I got things back from Dr. Colbert.